Welcome back to Scrap Paper and Philosophy 21. And today we're going to celebrate Maxwell's equations coming from Panda the Red because Panda the Red kicks my ass in latex. This is exactly what I mean. So here's Maxwell's equations. I'm going to celebrate them with coffee. And if you're not familiar with, well, if you're not familiar, you're a lost cause. But if you've seen this before, and I didn't remember exactly what these symbols were, but the dots are divergence, the symbol for divergence, and the cross product with this del operator is a symbol for curl. And of course, Panda the Red is going to explain all that in beautiful latex. But if you want a very good course in what these quantities mean, I would suggest Khan Academy Divergence of a Vector Field and Khan Academy Curl of a Vector Field. And that's going to take care of those two symbols. That said, let me go on another digression first. I made some promises to both viewers, which I have few, and random people. One of the promises was that there would be a Portuguese version of this, and the way I'm going to approach it is I'm just going to do one video in which I'll summarize the first 21 videos in English, and I'm going to call it Rascunho e Filosofia 1 a 21. If you're a fan of palindromes, you're welcome to watch it, I guess, when it comes out. Another promise is speed of light in media, because, well, what we want to do there is try to see if we can dabble in the arts of divining atomic structure from the speed of light in media, which we obviously get from the refraction index of light in known media with known atomic structures and molecular structure is what I refer to, because we don't only have the speed of light for random elements, we have the speed of light for random compounds. Um, well, they're not random. I mean, they're obviously important for some reason. Uh, the the Maxwell's equations is what were. I've had coffee, so maybe I can do this. Um, okay, let's start with the first one. The first one says that the divergence of the electric field is the charge density over this constant. So the reason why we don't care about this equation at all, because the charge density is going to be zero. And the reason why the charge density is going to be zero is that we're going to be looking at something like this, which is supposed to be an LC circuit. Here's the capacitor, right? Charge is going to form on the plates of the capacitor once this is powered, and that charge is going to get neutralized, not neutralized, but it's going to cause a current going through the inductor, and that current is going to overshoot the point where the capacitor is neutral. And so that's going to cause an oscillating current in the circuit. Well, maybe we have a coil here or something to transmit this oscillation to this circuit on the right. And this circuit on the right is an antenna. Well, it's not an antenna, come on, it's a drawing of an antenna. But tell you what, the the stationary hypothesis, which is that this this light is really uh, spinning. These electromagnetic waves are really spinning magnets perfectly at rest, with the center perfectly at rest with respect to vacuum. That kind of idea works very nicely with a circuit like this, because we can think. We can remember that there's no charge enclosed in any part of this contraption on the right. If we enclose the entire contraption, which includes the antenna, there's not going to be any net charge. There is going to be an oscillating charge, okay? There's going to be an oscillating charge, but there's not going to be any net charge. So that's how we get around the first equation. There's no net charge, so we're enclosing a charge density of 0. Okay. Second equation is the divergence of the B field equals 0, says that there are no magnetic monopoles. There's only magnetic dipoles. Every magnet has a north and a south pole, and the south pole eats up all the field lines from the north pole along the x-axis of the magnet, and you get a divergence equals 0. So I'm laughing because uh, you see, I'm saying that this there's this train of north and south poles going to the antenna. But what we really know is that there's a train of oscillating charges. So it's going to be a very good exercise to formalize all this in a computational example. But I'm going to promise that this for next time, because I really have to do the computation before I have the full-blown computational example for you. Anyway, the most important equations are going to be these two bottom equations, which say that the curl of the E field is the negative of the time derivative of the B field, and the curl of the B field is this constant in the j direction. I assume there's an ijk direction, but of course, maybe Panda the Red will clear that up later in the paper. But so anyway, um, there's a constant times this, and then there's a constant times the time derivative of the E field. Now let me go straight to the point, okay? Because we have a rotating magnet, we can draw the B field on every point of this rotation. Because we can draw the B field on every point of this rotation, we will always be able to calculate this bottom quantity, the curl of the B field. And once we calculate the curl of the B field, what we get is the time derivative of the E field, which is not the same thing. Not the same thing as getting the electric field, because we know the time derivative of the electric field, but we don't know yet the initial electric field to correct by this time derivative. So the way we are going to get that is from this quantity here, the time derivative of the B field. Now, the reason why we can calculate the time derivative of the B field, the reason why we can calculate this is that we have the B field as a given at any point of the rotation. The only thing that we have to keep in mind is two things, really. One is the frequency of the rotation, then we can calculate the time derivative. And the other, I guess, is the offset, what I'm calling an offset to this rotation, because, well, I don't know. It's either gonna turn out to be like a Planck rotation, so we can calculate this derivative. It's either going to be a Planck rotation, or it's going to be, um, well, how can we say this? Or we can parameterize this into some kind of uh, in some kind of meaningful way. Okay, so we're either going to parameterize this in some kind of meaningful way, or we're going to have uh, well, let me tell you right away what the meaningful way is. Uh, okay, let me pause for a minute because I think this presentation is getting a little confusing. Okay, now, while it is fair to say that I'm a little high on organic herbs right now, it is also fair to say that I just had two epiphanies that I want to share with you. Because at first glance, the electromagnetic wave is going to involve only these two equations right here. And the divergence of the E field is uh, zero because we don't have any charge. The divergence of the B field equals zero. We want to look a little closely at that one. Well, first of all, let me correct something I said earlier, which is that this J here is some component of a vector. No, J is an entire vector representing the current, as explained right here, in the presence of a charge function rho and an electric current J. That's going to be, in a computational example, that's going to be very doable because what we're going to be looking at is something that had an electric current in the first place, at least on the left-hand side of the picture, generating our electromagnetic wave on the right side of the picture. The antenna blows out the electromagnetic wave and goes flying off in space, where a receiving antenna somewhere out in the space is going to be incident upon this electromagnetic wave blown out by the transmission line. Anyway, so back to this. We have the B field perfectly defined at all points on the rotation of the spinning magnet. We can use that to calculate the time derivative of the electric field. We can establish what we mean by a differential time, have some scale that we use, and that's going to come up in a computational example. But we really can calculate this time derivative of the B field. There's going to be lots of things in physics that we can use to calculate this. So we effectively can get an initial condition for the electric field. Now, the tricky part with this second equation, the divergence of the B field equals zero, is that if we're imagining a spinning magnet with a rotation that propagates only in time, not in space, and here let me go into a whole rant because what we're really doing here is we're separating time from space. I'm going to make two claims. One is that Maxwell was unaware that energy equals Planck's constant times the frequency nu. And the other claim is that Einstein was unaware of all of quantum mechanics 1960s going forward, in particular the quantum mechanics regarding photon location. And for the quantum mechanics regarding the location of photons in a laboratory, I have a source. There he is. His name is Dr. Benjamin Schumacher. I watched his course in. He's from Kenyon College, but this is a course for adult education. I suppose continuing education. I don't know what you call it, but he explained the setup of these experiments really well in his quantum mechanics course, available in the teaching by I think it's the teaching company TTC. So there he is, Dr. Benjamin from Kenyon College, and he's going to tell us. Well, he's going to tell us that a photon is. He's gonna show us the experiments and explain the results about how a photon is in all positions at once in a grid of mirrors, an arrangement of mirrors and half mirrors placed upon the lab. The photon is at every single point in this arrangement at once until it is detected by as a random event in some part of this arrangement of mirrors and half mirrors. And this is a paradox, of course, because how can a single photon be seen to be experimentally measured to be in all places at the same time? And the way that the luminocentric principle is going to solve this paradox, is that it is really the motion of the lab that is generating any concept of velocity in the system. Okay. Uh, the motion of the lab, the once you have motion in the lab, then you have changing locations of the photon. The changing locations, the photon is really a location into itself. So the changing locations of the photon in the laboratory are due to the motion of the laboratory. That way we solve the paradox. As from the initial condition of the laboratory to the final condition where the photon was detected, you had only one way to assert this concept of motion, which is the motion of the laboratory, not the motion of the photon. And that solves the paradox. So, uh, uh, I mean, that's why we're going to have to do a computational example too, because maybe what I said makes no sense. And I'm also going to go into a digression with probabilities at the end of this video. But while we're doing simpler stuff here, uh, Einstein knew that the mass of a photon is proportional to 1 over the wavelength. He won the Nobel Prize for the photoelectric effect, so he knew about the interactions of photons with atoms. Uh, but the extrapolation being made here is that photons are stationary, and both Maxwell and Einstein would have missed it. Well, Maxwell missed it because he didn't know that he didn't know that the energy signature of photons is a frequency. And a frequency as an energy signature can only propagate in time. It cannot propagate in space. Uh, Einstein wouldn't have known how ironclad this kind of quantum mechanics is by the 21st century. So maybe he wouldn't have seen it either, because it really helps explain this this quantum mechanics. Um, but um, okay. Oh yes, and Einstein came up with space-time. So Einstein views the speed of light as as a conversion factor that really joins the concept of space and time together, but we want to unpack space from time. And the way we do that is that we say that waves in space will have their I wrote lambda. What I meant was amplitude. Why is the amplitude the wavelength? No, I should have I should have a norm here, right? Well, whatever. Waves in space will have amplitude as an energy signature. Now, the amplitude of a wave, what is it equal to? Well, if we have like a sine wave, then the wavelength is 2 pi, and the amplitude is the wavelength over 2 pi. The amplitude is 1, it's the wavelength over 2 pi. So at least in that case, I think we have wavelength and amplitude kind of being the same thing, or not. Absolutely not, because these are like different concepts. But the physics should be very clear. So even though what I wrote here is wrong, the physics should be very clear that in space we have amplitude waves. Okay, because waves propagating in space, they need to distort a medium, so they have amplitude. In time, waves don't need that. Their energy signature is not their amplitude, their energy signature is their frequency. Now, there I can write frequency as 1 over the wavelength. I don't know what I was doing in space. But in time, that's, you know, that's the energy signature. It's 1 over the wavelength, right? With the speed of light, multiplying that quantity as a conversion factor between space and time, we're going to have to look very closely at that. In particular, um, let's leave that as a digression right now and go back to Maxwell's equations. So, when we have a rotating magnet, and we're calling that an electromagnetic wave, for there to be a displacement in time, because we're saying that the rotating magnet, it propagates, the motion is propagating in time, it's not propagating in space. So for there to be a propagation in time, then it's not entirely clear for me right now that this is true, that this divergence of the B field equals 0. Because in time, the magnet, it cannot it's leaving behind it's leaving behind fields in time. It's not eating it's not eating all its fields properly as it emits them. So this is going to be a challenge. The first equation, which is known as Gauss's law, is going to be easier to deal with because we know we're not enclosing any charge, especially in vacuum. In fact, the first equation is probably going to be very useful when we examine interactions between these electromagnetic waves and atoms. Because, well, the atom is not, an electrically neutral atom isn't enclosing any charge. But the region in space, if you imagine that The spinning magnet has a region in space where these equations apply. They have a boundary where these equations apply. So, within that boundary, then we have at some point we have an E field that is significant coming from an electron on the outer reaches of the atom, because the proton is like, I don't know, it's lost in space in the middle of the atom somewhere else. I think I already told you that J is electric current, which is going to be easier to deal with if we imagine the entire LC circuit generating the electromagnetic wave, but we can do that in a computational example later. Uh, so next I want to go into some digressions, and I'm going to start with crediting this amazing person, Kiza Vorobianinov, because Kiza, when not tearing Tyler Hendricks to shreds, God knows why, I have no idea. But maybe it's because Tyler Hendricks believes, I don't know why. But anyway, Kiza is very, her beef with establishment astronomy has to do with the relativistic Doppler effect. So eventually we want to do that too. And just to show you why, it's not only Kiza that's like seen how the relativistic Doppler effect, it's got some unsolved paradoxes, let me put it that way. So we want to look very closely at that. But here's another. Here's a comment about how Hubble's constant cannot be constant. And the way he shows this is by talking about the redshift, which is a concept from the relativistic Doppler effect. And there he's showing how the redshift, it doesn't result in linearity, which would be in the required linearity for Hubble's constant to be constant. And so there's a lot of, it's like an elephant in the room, this relativistic Doppler effect. And I don't want to go into it right now because to me it seems like there's like less advanced topics I can discuss within within this idea that we can separate space from time. So, but I hope to get there eventually with this this stuff that Kiza was talking about. And I want to credit Kiza by pointing me in the wrong direction. No, I want to credit Kiza with pointing me in the right direction. Excuse me, Kiza, because one of the things Kiza eventually says down who knows where uh, is that uh, well, is that there's no such thing as negative numbers in nature. There's only positive numbers in nature. And the reason why that turns out to be really interesting is that we think of negative, we like negative numbers. I mean, when we have a checking account that we can draw upon, that we can overdraw, and with overdrawing rights, you know, we like the negative numbers because then we can run a negative checking account. But Kiza might be right. Maybe negative numbers do not exist in nature. And so to model nature, we're gonna need the square root of -1 but we're not going to need the negative numbers. I mean, it, if there's only positive, if we're dealing with atomic structure, we're dealing with uh, shapes and things. We're not dealing with negative numbers. The only thing that allows negative numbers in this system is the passage of time, because with the passage of time, there's going to be the concept of decrement. So we can get around negative numbers by going from, say, something like this. Okay, probability of red ball in the next 10 draws equals 1 minus probability of no red ball in the next 10 draws. And then we go from there to probability of red ball in the next 10 draws equals probability that there's a red ball, and there is, that's a statement of existence, minus the probability that there's no red ball in the next 10 draws. I call this a statement of absence. So the statement of presence equals the statement of existence. The difference, the statement of presence is the difference between the statement of existence and the statement of absence, but we don't want negative signs at all, so we're going to replace this negative sign by plus I squared, and the probability that a red ball comes next, or comes in the next 10 draws, or comes whenever you're calculating that probability, is going to be the probability that there's a red ball in the universe plus I squared times, it's not coming next, and this it's not and then I go into a whole rant about probabilities, and it goes on and on and on in my little, I wrote this when, I realized as I was reading it that I wrote this when Obama was president of the United States. I know it because I address it to his science officer. But and of course I never wrote, I never do a write up. But this rant about probabilities was probably about one of something that uh, something that I saw, and I don't answer what are the units of probability, but the units of decrement, I will answer to you right now. The units of decrement are time units. Okay, there's no decrement in the universe without the passage of time. Oh, there's only positive stuff in the universe without the passage of time. And thanks for watching, and I hope I didn't bore you to death. See you next time.